so it says for all real numbers x, y can't be 0. The only reason y can't be 0 is we got a y in the denominator, so it's just reminding us y can't be 0. Find the maximum value of this function along the trace y equals 1. So we're not required to do this in Desmos, so when we sit down for the test, we probably won't do this at all. However, I'm just going to graph this just so we can visualize exactly what's happening. So this is the surface, and we are looking at this surface along the trace y equals 1. You're going to get some sort of band. So let's go ahead and plug in y equals 1. So my notation, I can do g of x comma 1 is what's going in for y. So I got x squared over 1 plus 6x times 1 squared plus 8 times 1 to the fifth. So I'm looking at that surface along that rubber band. So while this is now a function of only one variable, I can call this f of x. Now it's just a single count 1 function. X squared plus 6x plus 8. So now I have the curve, that rubber band. How can I find the critical point along that band now?
Set to 0, set f of x to 0.
Do the derivative and then set it to
So the
zero.
derivative.
That's right. The derivative has been set to 0. Sorry. 6.
So I've got an x value for the critical point. It does tell me to express my answer as an ordered triple. So I need x, y, z, but I only have x. So remind me, if x is negative 3, how do I find my y?
Well, we get x back into the original function and then solve for y.
Could. I don't disagree with that. But don't
No,
forget,
y
we're
equals
looking
1,
along
yeah.
the trace y equals 1.
Right.
So no matter where you go, y is 1.
Right.
And now the z is not too bad. I feel like we're pretty confident in that one. Now I just want to find g of negative 3 comma 1. So this is actually what we were doing in that optimization lesson where we were looking along kind of the boundaries and we could plug that in. So here they're asking you to optimize, so find the maximum, this could have been a minimum too. Find the maximum or minimum value along the trace. And when you're looking at a curve along a trace, you can see different shapes. You can see maximums, minimums. All right. Please ask questions on number 1. Number 2, values of the function h and its partial derivatives at select points are given in the table below. So just kind of quickly glancing at the table, it looks like I've got different points. These are all inputs. And it's going to give me the function's value, partial with respect to x, partial with respect to y, my second partials for each, and only one of my mixed partials. And I think we quickly remember that, oh, it's kind of redundant to have the other mixed partial because those would be the same thing. The actual question says, write an equation of the plane tangent to the function at the point 3, 2. So I just flipped through my notes, and I'm just going to write down what we had in our notes. A tangent plane is z minus the z coordinate equals your partial derivative times x minus the x coordinate. We'll call that a. Plus the partial at y times y minus the y coordinate. So, just so we can see it, it's still like Calc 1, the slope times x minus the x coordinate. Now in Calc 3, we've just got a slope times y minus the y coordinate. So if we really want to think of this, in space, you have the point, it wants it at 3, 2, 3, 2, what is the z coordinate? This is saying h of x, y, that's just the z coordinate. And that's 5. And then if we just want to be super explicit and say the partial with respect to x at that point is -3. The partial with respect to y at that point is 4. So now dropping this in my formula, I've got z minus the z coordinate equals the partial with respect to x times x minus 3 plus the partial with respect to y times y minus 2. And this is where we have to make the decision of what do we want to do with this equation. If you guys remember from practice test 1, it wanted us to find the normal vector, so we wrote it in that standard form. This question wants me to do something different with the tangent plane. It's saying, then use your plane to approximate a point nearby. So I'm still going to go ahead and distribute and clean up just a little bit, but I'm going to leave this as z equals something. I'm going to add the 5 over, minus 3x plus 9, plus 4y minus 8. So again, once you've kind of cleaned it up, lots of different ways that you can write it, I'm going to leave this as z equals something because this tangent plane becomes an approximation of what the surface is doing at that point. So I have no idea what this function h looks like, but I can say that function behaves like negative 3x plus 4y plus 6 near the point 3, 2. I'm going to just pause there for a second because conceptually that's the leap for this problem that we have to make. We've got some sort of surface, you make a tangent plane, and we're saying, I don't know what the surface looks like, but around that point where you're tangent, that tangent plane becomes an approximation. So now if I want to approximate a point next door, like 3.2, 1.8, then I can just go ahead and plug that in. Let's just go right there. Please ask questions for 2.
Yeah, question. So, you got a scalar answer. You didn't get a vector. Got a scalar.
So, like how I grabbed the normal vector in practice test 1.
Mm-hmm.
So in practice test 1, the question was make a tangent plane, same as this one. But then it was just asking for the normal vector to the plane, which we would have to rearrange it in a slightly different order. Because I want to use this as an approximation, you do want to leave this as z equals something. So what it's asking you to do with the plane will decide how you want to clean this up.
And you're asking for just the point near there, near the tangent plane.
You're saying, so yes, so the point that they're asking you to find the tangent plane at, they actually might not have even told me the plane 3, 2. They might have asked me to just approximate h of 3.2, 1.8, and I would have made the decision, well, that point seems to be really close to what I'm trying to approximate.
What is like another way that it might be asked, like, to show it as, besides from just like the negative 3x plus 4y plus 6?
You're saying another way to show this?
Well, like you were saying, like from normal or showing standard or showing local, like what would be another way that we would see that?
I just want to make sure. Another way to see a different problem type or see the equation of the plane.
The equation.
So right now we have z equals negative 3x plus 4y plus 6. If you write this in that standard form, moving this over, moving that over, this is the standard form.
Okay.
Practice test 1 asked, what is the normal vector of the tangent plane? And you could grab it from this form, but notice you can't grab it from that form.
Okay, understand.
All right, number 3. Consider the paraboloid defined by this equation. Write a function of 2 variables that can be used to find the minimum distance from some point, 5, 5, 0, to the parabola. Do not solve for the minimum distance. So this is an optimization problem. But it's kind of a softball one in that it doesn't actually want you to do the math. It's just saying get the setup, write the equation that you're going to use, but then don't actually solve for the minimum distance. So we said optimization, we need 2 equations, an optimization equation, and a constraint. we thinking for an optimization equation? Wants us to find the minimum distance. So if I want the minimum distance, I'm trying to optimize the distance between 2 points. So I'm thinking distance formula. My 2 points being 5, 5, 0. Got that one. And the second point on the paraboloid. I don't know what the point is, so it's going to be some unknown point x, y, z. So the thing that I want to optimize is the distance between these 2 points. So x minus 5 squared plus y minus 5 squared plus, I'm going to write it just for emphasis, z minus 0 squared. That is the thing that I want to optimize. If I can find the minimum of that function, that would be the smallest distance between those 2 points. But there is always something holding me back. There's always some sort of constraint in the problem. And just to give you a quick reminder of how that's going to work. It's going to end up being a variable equals something. And then you can substitute that into your optimization equation to make it in terms of only 2 variables. And what is my constraint?
Z equals x squared plus y squared.
Yes. So just grabbing the equation of the paraboloid that they gave me, I want to plug something in for z so that I'm only left with x and y for the whole equation. Well, if I just take 2 seconds and solve for z, then z equals x squared plus y squared. No. And if z equals x squared plus y squared, then I can just drop that into my equation here. So now in those full optimization problems that we were doing, we would then take that formula, find the critical point by taking partial derivatives, but this says do not solve for the minimum distance. And that is how you would see it on the exam. Just show me the setup, show how these optimization problems work, get a setup from the prompt, get a constraint, and reading the prompt one more time, it says write a function of 2 variables, and it should be true that this is a function of only 2 variables, x and y. Questions? Number 4. Verify that the function z equals x to the third minus 3xy squared satisfies the quote-unquote partial differential equation. Now, if we're thinking, I didn't take partial differential equations yet, it's okay. Although we have not talked about this at all, it actually turns out to not be that bad of a problem. This is just saying, show that your second partial with respect to x plus your second partial with respect to y equals 0. That's it. Find your second partials, add them together, show that it equals 0. The only thing that is going to slow us down here is simply the notation. This is saying the second partial with respect to x, then x. So another way of writing this would be like that. And don't forget, put a huge star. We read these right to left. This is the partial derivative with respect to x, then x. So in this notation, we go right to left. But in our other one, where we write kind of the subscripts, x, say y, then we read left to right here, x, then y. I'm going to give you guys a good 60-ish seconds to find your second partials with respect to x, then with respect to y. It should be true that when you add them together, you get 0. You guys are going to like problems like this because you know the quote-unquote answer. You just need to show that it works out. So I took the partial derivative with respect to x. So I get 3x squared. Don't forget anything not involving x is treated as a constant. So the y squared will come along for the ride. So that would be negative 6x. Oh, I'm sorry. Negative 3y squared. Taking the derivative with respect to y. And x to the third is just a constant, so it drops off. And over here, that would be negative 6xy. Now take the partial again with respect to x. So I get 6x. With respect to y again, negative 6x. And this is just saying show that when you add those two things together, you get 0. So again, the heavy lifting there is just the notation, remembering the notation that this is the second partial with respect to x, then x again. Questions? Number 5, find the critical points of the function it blurry for you guys too?
Yeah, no, but. There we go.
Fine. Find the critical points of the function. Write your answers as ordered triples. You do not need to classify the critical points. I will figure out what's happening. All right, so I'm thinking critical points. How do I find the critical points?
First derivative is 0.
Little more. You're not wrong, good.
Oh, take your partials
Take your partial derivative.
and just send 0.
Yeah. So you got to take partial with respect to x, partial with respect to y. Both of them have to equal 0. Little step table. Someone walk me through it. What can I do now?
Where you at? You solve for x and your h of x, or don't, or solve for x and your h of y.
You
I get
could, and there's nothing wrong with that. But then you get some fractions.
Yeah.
If I can help it, I'm going to solve for the thing that has a coefficient of 1.
Yeah. Okay. Easy. Okay.
So now I got x squared minus y equals 0. So y equals x squared.
Oh, okay.
You could have just divided both sides by 3. You'd still land on this.
Same thing, yeah.
And now what do I do with this information that y equals x squared?
Plug it into your h of y.
Yep. So negative 3x plus 2y equals 0. I recognize that there's an x in both of those
Right,
terms.
x is 0. 1, 9.
So now we just need to stay organized. I need an x from one, a y from the other. So if I've got x is 0 over here, then I need a y from over here. And it's saying y is just whatever x is squared. So 0, comma, grab an x from over here, 3 over 2, comma, yep, I know y is whatever x is squared. Rereading the prompt, write your answers in the form x, comma, y, comma, z. So I need the z coordinate now. No worries, we've got Desmos in front of us, we've got a calculator. I can just type in the function. And I can just type h of 0, comma 0. And I can type h of 3 over 2, comma 9 over 4. So now, because we have Desmos in front of us, why don't we actually, let's see how we did it. 0, 0, 0, 3 over 2, 9 over 4, negative 27 over 16. So I've got this point here, and that is definitely a critical point. Classify this critical point here.
That looks like a saddle.
That is a saddle, yes. Just a reminder, if you travel along this way, you get a minimum. But if you traveled along this way, you get a maximum. And the other point in blue, that looks pretty good. What kind of a critical point is that?
Local minimum.
All right, please ask questions about the previous one.
So then our final answer is 0, 0,
True, and h of 0, 0 is 0. The other one, 3 over 2, comma 9 over 4, comma, yes, h of 3 over 2, comma 9 over 4. All right, number 1. The function p of a comma b represents the revenue in dollars of a grocery store that has sold A apples and B bananas. Given the partial derivative with respect to A at 4 comma 2 equals 3, which of the following best interprets the meaning of the value in the context of the problem? So I'm going to give you guys just about a minute or so to read through the options, find the best one. Alright, so partial derivative with respect to A means if I increase in the x direction, or if I head in the positive x direction, in this case the positive A direction, I get a positive number, so I should be increasing. Which one of those do we think best describes what's happening?
D?
I like D. It's saying the revenue increased by $3, so there's my increase, my derivative is positive, for $3 for each additional apple. So if you head in the positive apple direction, then your function is going to increase by $3 when 4 apples and 2 bananas is sold. All right, number 2. Particle moves through 3-dimensional space with the velocity vector given by this thing. So this is my velocity. It says at t equals 0, the particle is at the position 5, 6, 7. Using a linear approximation, estimate the position of the particle at t equals 5. So this is kind of what we did for the tangent plane. I've got some sort of curve. We're going to make a tangent line, except in 3D. And then I'm going to use that tangent line to approximate a point right next door. And since that tangent line behaves like this space curve will, I can just use this line to roughly approximate the position. So to build a line, I need a point, and the point was given to me as 5, 6, 7. And now I need a slope, but since we're in 3D, that's our direction vector. How can I find the direction that this particle is moving in? That is the velocity vector. The velocity vector is, in this case, a 3D vector that gives you the direction that we're traveling. Well, what time? Well, the point that we had was at t equals 0. So if we find v of 0, that